Okay, so we're on to lesson 15, the final lesson in electricity, and we're dealing with AC and DC, okay, or particularly AC. So remember, direct current, which implies direct voltage, is when the current and the voltage stay the same at all times, okay, and that's normally what we use, and that's normally what we would have been doing in current electricity all the way along. So we'll just draw the graph associated with it. Okay, so we'd have current against time, and quite simply, as time goes on, the current stays exactly the same. That's supposed to be a straight line. Okay, as time goes on, current stays exactly the same. Right, now, better. Okay, alternating current is different. Okay, and alternating current, there's 2 points alternating current. It changes direction, but it also goes from plus to minus. So there are two very important points. Okay, so we basically would have something like this. You're all well familiar with sine graphs in maths at this stage. So that is your alternating current. So it keeps changing from a peak value to another peak value, a negative peak, positive peak, negative peak, in this pattern. Okay, and that's what we have. That's what we have in mains electricity, and we'll see why that is in a minute. Okay, alternating current, very useful type of current, as we can see. Now, there is a problem with alternating current, of course, in that if I asked you what's the average current for alternating current, it will always be 0. Okay, because obviously the pluses will cancel the minuses, no matter how high the peaks and the troughs are. Okay, it will always be 0. So we can't deal with that. So what we do is we get what's called a root mean squared current. Okay, and it makes quite a big sense. Okay, it's called an RMS current, root mean square. Okay, and what we do is we square all the values, so now they're all plus, there's no more longer plus or minuses. We get the mean or the average of all of those, so we have the average of the squares, and then we square root back. So that removes the issue of negative values. So we don't have to worry about where it comes from, but that's what RMS means. It makes sense. So RMS is a root mean squared. Now it's not halfway, it's more than halfway because of the shape of the sine curve. Okay, we don't need to go into detail what it is because we have a value. Okay, we have a formula. Okay, that the RMS current and indeed the RMS voltage is the peak, okay, divided by, and this constant you have to remember the square root, well you don't because it's in the tables, but you will remember it anyhow, square root of 2. Okay, so to go from the peak to the RMS you divide by root 2. Now obviously the RMS is going to be less than the peak, so if you're going from the RMS to the peak, well you're clearly going to multiply by root 2. So effectively you can take it as formula if you like, or you can take it as the multiplying factor is root 2. So peak to RMS divided by root 2, RMS to peak, multiply by root 2. Okay, so that's where we're at. Okay, so we'll do a few calculations on those in the next clip. Right, now, okay, now, why bother with alternating current? Well, the reason we bother with alternating current is to do with electromagnetic induction. Okay, so let's go back to our mutual induction situation. Okay, we have this situation. Okay, right, so circuit 1, power supply, circuit 2, right, and it's a DC power supply, remember it's DC, direct current, and circuit 2, no power supply, so there won't be an EMF induced or current flows unless we have, unless we're turning it on and off or doing something like that, or moving things. You want to be moving things, right? So what can you do? Okay, so at the moment there is a magnetic field from this because there's current going through it. Okay, so we just draw it. Now remember, magnetic field goes through like that, goes through like this. Okay, right, and so on. So just draw a few bits like that. Okay, right. So you have a magnetic field here that is cutting the secondary coil, but it's not a changing magnetic field, so there's no EMF induced. Remember, that's the crucial point, the changing magnetic field. It is not changing. But what if we do this? If we put in AC here, okay, but what's happening with AC? Okay, with AC, and you're going to see this in a lovely clip later, with AC, every 1/50th of a second, this swaps, just changes direction. It keeps changing. So if there's a changing alternating current, there's a changing magnetic field all of the time. Therefore, there's a changing magnetic field all of the time cutting that. So there's always an EMF induced there. And the EMF induced will also be alternating. And it will actually depend on the number of turns in the primary and the number of turns in the secondary. And this is how we bring voltages up and voltages down using what's called a transformer. Okay, so let's have a look. So for a transformer, the way we draw them, even though in reality they're usually not like this, the way we draw them is we draw what we call the primary coil here and the secondary coil, and I'm going to get more turns in the secondary coil here. Okay, that's what we do. That's step one. Okay, and right, this is going to be an AC input. This is the primary coil going in, primary school, first one. Secondary coming out. Okay, now primary to secondary, we want the magnetic flux from here cutting this. Okay, and we saw earlier in the experimental mutual induction that if we put in a soft iron core, a laminated soft iron core, suddenly it all goes well. Okay, you get much greater flux linkage. So these will always be wrapped on the same iron core. Okay, and it's a laminated to reduce energy losses, soft iron core. Okay, so there we go, we're in that position, right? So what we have here is that there'll be an alternating current here, there'll be an alternating magnetic field from this coil, cutting this coil. It'll stay in the iron core effectively, okay, cutting this coil. So there'll be an induced EMF in this coil, okay, and we won't go into the maths of it, but the induced EMF, the size of the induced EMF will depend on the ratio between the number of turns of primary and number of turns in secondary, as we'll see in a minute. Okay, that's a calculation we look at in the next clip. Right? Okay, so that's the primary, that's the secondary. Okay, now, so that's how it works. So let's go through it. Let's go through step by step. Alternating current in the primary, changing current in the primary, therefore changing magnetic field from the primary, changing magnetic field from the primary, cutting the secondary because of good flux linkage, right? EMF induced in the secondary, current flows in the secondary, and the current flow in the secondary is a alternating current. Okay, and the size of the voltage between here and here depends on the ratio of the two of those. Okay, so there you have primary and secondary. Now, okay. So that's how the transformer operates. Okay, so we look at it in your notes, and there is a example in a clip that you'll see now in a minute as well. Okay. Okay. So third step. Okay, so third and final step is to do with what effect AC has on different devices. So we're going to look at the different devices. Okay, a resistor, okay, a diode, a capacitor, and a coil. Okay, now DC or AC? Okay, so DC and AC. Okay, so first of all, a resistor, it has resistance in DC, it has the same resistance in AC. For a resistor, there is no induced EMF or anything like that, so therefore no effect, no difference. Okay, the diode, okay, the diode, right, remember now, okay, flows in one direction for DC. Okay, for AC, okay, AC flows in two directions, so basically it will work half at a time for each cycle. So current will flow, but it will be a smaller current. Okay, capacitor. Okay, so we know for a capacitor, okay, it blocks DC because a current flows for a very short period until the plates are effectively full, until the capacitor is at the same voltage as the power supply, and then it stops. So effectively it blocks DC, allows current to flow until it's charged and then blocks it. For AC, effectively keeps charging and discharging and charging and discharging the two plates as they go from plus to minus, so a current flows. That's important. So current flows for AC in a capacitor, current doesn't flow for DC. Okay, doesn't flow for DC, so blocks DC. Now that's what's the most interesting one, and the one we've just looked at is the coil. Okay, now coil is also known as an inductor sometimes, and it's sometimes even known as a choke. Okay, right. Now for AC, think about it. For DC, it just has its resistance. Okay, so it has its resistance. So it's what we call ohmic resistance. So it has a resistance like a resistor would, and we call it the ohmic resistance because it's linked into the resistor. Okay, but for AC, it still has that ohmic resistance like up here, but it also has the fact that if there's AC, there's going to be a changing magnetic flux cutting that coil, and it's going to be an induced EMF in that coil. Now let's go through this because it's really interesting. Okay, so there's a changing so it's AC, so a changing magnetic field. The changing magnetic field is cutting itself, it's cutting the coil, so it's inducing an EMF in the coil. It's inducing an EMF in the coil, okay, and that EMF opposes what's causing it, so it goes against the applied voltage. So if the applied voltage is 6 volts and the induced EMF is 1 volt, it'll be minus 1 volt. So effectively that reduces the effective voltage, it reduces the effective voltage, so it effectively acts as another resistor. Okay, so we say plus the resistance, that kind of in inverted commas, due to, sorry if I lost that, okay, plus the resistance due to induced EMF. So let's recap on the four of them. Okay, for a resistor, DC and AC, no difference. Okay, the same current will flow in both. For a diode, current flow in one direction only. For DC, in AC, it will flow in both directions. Okay, so it will be flowing half of the time both times. Okay, so it will flow all of the time. Okay, but it will be a smaller current than the equivalent DC. Okay, for a capacitor, blocks DC. It blocks DC. DC current only flows until it is fully charged or until its voltage is the same as the voltage of the power supply. So it blocks DC. AC current flows all the time because it keeps charging and discharging the opposite plates, as we saw back when we were doing capacitance. Okay, and finally for the coil, okay, in both cases there is a resistance to the coil. We call that the ohmic resistance. It will be the same for both, but there's an extra resistance due to the induced EMF, what we call induced EMF. Another name for that is the back EMF. So any induced EMF that opposes the change causing it, in this case the change causing it is a voltage, so it's a negative voltage, so it reduces the voltage of the circuit, so therefore acts as another resistor, so it's an extra resistance. Okay, so that's all of those. So effectively that's AC. Okay, so we have to be able to change from peak to RMS voltages. We need to be able to operate, understand why and how we use a transformer. Okay, there is, in your notes, there is factors that affect the efficiency of a transformer. Make sure you know those. They're in a 2-minute clip at the end that you'll be looking at in a minute anyhow. Okay, and other than that, that's it. That's AC, right? Okay, I'm going to do some calculations now as well, and look at a couple of clips beyond that as well. They're both worth looking at, and then you'll be in good shape after that. Okay, thanks a minute. Bye bye.